Hi, this video is an exploration of the transmission coefficient. Um, in particular, for the case of tunneling through a rectangular barrier potential. And understanding this transmission coefficient, which I'm going to call capital T, it is the basis for understanding a technology like the scanning tunneling microscope. And the scanning tunneling microscope is often referred to as the STM. It's a microscope that can see extremely small features, like features on the scale of a fraction of a nanometer, right? So this is definitely atomic size. So it's a scanning tunneling microscope that gives you a resolution, right, that sees within, it doesn't see within an atom. What it does is it sees inside the scale of the size of the atom. Okay, so it turns out, the previous couple of videos explored how or where you would get something called a transmission coefficient. I'm going to cut to the chase and write the answer down. In order to get to this answer, though, you essentially follow the steps that I outlined in the previous videos, and then you do a whole bunch of algebra, right? So when you do all this algebra, which it maybe would take somebody 30 minutes, 30 minutes to 2 hours, right? You're just sort of force fitting into this shape, which happens to be really, really efficient. So there is an exact formula for the transmission coefficient. It's a function of the width of the barrier. And we're going to say that it's a function of the energy of the incident particles, right? Also in this formula, though, is the barrier's height. So these three details are actually in the formula for the transmission coefficient, but we only say that we vary the energy of the incoming particles, and we vary how big the gap is in terms of its width, but we do not vary the height of the barrier. We say that the barrier's height is sort of like an independent issue. It's an issue it has more to do with maybe the materials involved. So here are the things that we might imagine we can control in an experiment or inside of a technology, right? And the expression, it actually does have u sub 0 inside of it, because beta is this factor. It's got dimensions of 1 over length, but it actually depends both on E and U naught, and also the mass of the incoming particles, right? So that beta coefficient is full of physics details, right? Particular experimental setup details. W is the width. Gamma is a particular combination. It's a convenience to use this symbol called gamma. It's beta. So beta is, I just discussed it. It depends on U naught, E, the mass of the particle. It's got H bar in it, right? K also has all those details, but K, remember, is the wave number of the basically the incoming and the transmitted wave functions. So K was the wave number. You can see beta and K in the previous video. But anyway, so this is the exact transmission coefficient after a whole bunch of algebra. Now, if you think about stuff a little bit, you can come up with this approximation, which approximates this form up here. And this approximation, if you look at it, is pretty basic. It's simple to understand. I've got a number 16. I've got the ratio of the energy to the potential energy. So this is a fraction. It'll be less than 1 for our tunneling problems, right? Tunneling is when the energy is classically forbidden to transmit, or our particles are classically forbidden to transmit. That's called the tunneling situation. And then it's 1 minus that fraction. But then it's got this exponential, e raised to the minus 2 beta w, right? So the reason for this exponential can kind of be seen based on these functions, which I haven't described yet. You may have run into this in a math class or even another like engineering or physics class, but they're called the hyperbolic cosine and hyperbolic sine functions. And here they are in the denominator added to each other with this relative factor, gamma over 2 squared. But this hyperbolic cosine is squared, and its argument is beta times w, where w is the width, beta is that inverse length scaling that I described already. So, but anyways, if you look at the hyperbolic cosine and hyperbolic sine, this is how they're defined, right? These are the definitions. So hyperbolic cosine and sine definitions, they're written in terms of a linear combination of e raised to the argument and e raised to the negative of the argument. So these are pretty interesting. They kind of parallel the Euler formula for the sine and the cosine written in terms of an imaginary argument to an exponential. But these are written this way. So if you look at these functions, what's interesting about them, the reason why they're called hyperbolic cosine and hyperbolic sine is because their derivatives behave almost like sine and cosine. If you take the derivative of the hyperbolic cosine, you get the sine function, or the hyperbolic sine. And if you take the derivative of the hyperbolic sine, you get the hyperbolic cosine instead. But what you don't get is the relative minus sign, right? You know that the derivative of the cosine function gives the negative of the sine function, but not true for the hyperbolic cosine and sine. Also, the double derivative of hyperbolic sine and hyperbolic cosine just give hyperbolic sine and hyperbolic cosine back. So I made a mistake here. This is meant to be hyperbolic cosine. All right. This approximation that I alluded to right here, right, where this simple looking form, it's got this exponential that's width dependent, right? The only width dependence is in this exponential, right? There's no width dependence anywhere else in the other prefactors. But the approximation is good when the barrier is tall and the barrier is wide, right? So the approximation is good for the case of very small transmission coefficients. And what I've got is an example where we do have very small transmission coefficients. So small transmission coefficient means that when I calculate t, it's going to have a very small number. And that small number, let me show you quickly the example. The examples that we're going to have are that the transmission coefficient is like 10 to the minus 36, or 10 to the minus 25, or 10 to the minus 4, or 10 to the minus 7. But this is the sort of small, well, this is what I mean by small. I don't mean small in the sense of like 10 to the minus 1 or even 10 to the minus 2. I'm talking 10 to the minus 40 or 10 to the minus 50 or 10 to the minus 10, you know? So those are the types of transmission coefficients that this approximation is good for. So let's study this. So here is this approximate form. I just rewrote it. Here is the meaning of that coefficient beta. You can see it's got the mass of our incident particles. It's got the quantum of action, this thing called Planck's constant. It's got the difference in the potential energy and the kinetic energy, or the total energy, really. So, yeah. So if you look at all of the units in here and you look at the combination of units, what you're going to find for beta is inverse length units. Like its units, it'll be some number, right? Depending on the size of U naught and E and the mass. But it's going to come out to be like 1 over meters or 1 over nanometers or something like that. So that makes sense because the argument of this exponential is not allowed to have units. Physically, having the argument have units physically doesn't make any sense at all. Yeah, so physicists never allow the expression that has an exponential. Physicists never allow the arguments of exponentials or natural logs or even sines and cosines to ultimately have units that don't cancel out. Notice that this transmission coefficient overall doesn't have units either. It's 16 times an energy over an energy multiplied by 1 minus an energy over an energy, so everything here is unitless. And then I'm multiplying by the result of an exponential of a number without units, has no units. There's no units in this expression. It's purely a fraction, which we understand as a percent. I see when I calculate a transmission coefficient, I'm going to put a percent symbol on it. Okay, so I want us to study e to the minus 2 beta w. When you go and you put in electron volt type values here, you're going to put in a hyper tiny mass, right? If we're talking about the electron, it's 10 to the minus 30 kilograms, right? And if you put in h bar, which is also small, in the end, you're going to have beta being kind of a small number, or a small inverse length. W is a small length. It's on the order of nanometers. So you're going to have things that look like this or this. You're going to have e raised to the minus 80, e raised to the minus 50, and a calculator, right? If you want to calculate things, like actually, calculate values, have numbers show up that you can understand, your calculator will not help. That is, your calculator cannot tell you the difference between e to the minus 80 and e to the minus 50, even though they're incredibly different. E to the minus 80 is much smaller than e to the minus 50. The way that we do this is with a clever trick. So here's the trick. It's to remember that e raised to a number called y is equal to 10 raised to that same number but divided by the natural log of 10. And the reason this is true is really easy to see if you just take the natural log of both sides. So let's assume it's true and take the natural log. So the natural log of e to the y equals the natural log of this thing, 10 raised to the y over the natural log of 10, right? And the natural log of e to the y is just y, because the natural log and the exponential are inverse functions, so they undo each other and spit down the argument. And here, we have to take a couple of steps. The natural log of a number raised to another number is you just take this number and take it outside of the argument of the natural log and multiply. So it's y over the natural log of 10 multiplied by the natural log of 10. And you can see how this works. The natural log of 10 cancels and you get y equals to y. So my assumption was the right assumption. The assumption leads to what you might say is a triviality. So that means my assumption was true. So I assumed this was true. My assumption was the right assumption. So that's our trick. But what this does is it converts something like e to the minus 80 into 10 raised to minus 80 divided by the natural log of 10. Your calculator easily calculates the natural log of 10. Your calculator easily calculates 80 divided by the natural log of 10. So if you look at what this kind of number is, I'm going to calculate it on my calculator really quick. So I'm going to do 80 divided by the natural log of 10, and that's equal to about 35. So this is 10 raised to the minus 34.74, right? So that's what this is. And so here is a little bit extra clever trick, right? this is 10 to the minus 34 times 10 to the negative 0.74. And the reason why this is interesting is because this is scientific notation. So it automatically gives you the scientific notation. So it automatically gives you this scientific notation multiplied by a number, right? So here's so the scientific notation comes out naturally, and then you multiply by some number. So this is, right, if you calculate 10 to the negative 0.74, let me do that. So it'll be 10 raised to the 0.74 equals, and then I invert that. So let's see, second answer inverse equals 0.1819 or 0.182. So this is 0.182 times 10 to the minus 34, right? So this thing right here is 0.182. And if I want to understand this in terms of a percent, this looks like, for example, 18.2 times 10 to the minus 34%. So that's how I'm going to do this. Every time I calculate this thing, I'm going to use this technique. All right, and I can get this prefactor, this 18.2. Of course, the 18.2, right, pretend this was the 18.2% times 10 to the minus 34 or whatever it was. It gets multiplied by this stuff as well. So you got a couple of calculations to do with your calculator, but that's the trick. But that's all to say, I want to see what this thing does. So I first need to learn how to use it, how to make it do the thing it does. But then I'm going to make it do the thing it does with some data and check out what I get. So here's the idea. I'm going to consider a potential barrier that's 10 electron volts high. But then I'm going to try out different widths, 5 nanometers wide, 1 nanometer wide. And I'm going to try out different energies, 7 electron volts, which is less than 10, or 9 electron volts, also less than 10. And so the barriers that I'm trying out look like this. I can try out a 1 nanometer wide, or I can try out a 5 nanometer wide, but it's in both cases, it's 10 electron volts tall. And in these two cases, I can study either 7 electron volts for an energy or 9 electron volts, which is right underneath the top of the barrier for an energy, right? So I'm trying out these two different energies. And so I can have two different widths, right? This is the 5 nanometer width, and this is the 1 nanometer width. And the answers are kind of crazy. So check this out. These are the wide barriers at two different energies, right? So if you're at 7 electron volts, that is your 3 electron volts from the top, this is your percent to be transmitted, which looks so similar to 0. But if you keep the same barrier height, but fire higher energy particles at it, they're still not classically able to go over the top. But what happens is, look at how different the transmission coefficient is. It's 10 to the minus 36, and then it becomes 10 to the minus 25. And if you think about it, that's a factor of 10 to the 10th difference, right? That's a huge difference in transmission coefficient just based on a small change in energy. But let's go and look at the really narrow barrier. 1 nanometer. And if you look at the narrow barrier, look at what happens. You're way more likely to transmit compared to the wide barrier. It's still true that changing the energy gives you a little bit less wait, do I have that right way around? 10 to the minus 4. I may have miscopied something. I actually copied this example. Oh, I'm curious about this. Yeah, so this might be something I need to think about a little bit. But anyways, I'm going to quote what I am getting here. So this is coming from Openstax, University Physics, Volume 3. It's chapter, what chapter is this? 7. It's an example if you care to go look at it. But the point is qualitatively, with a wide barrier, you basically aren't going to see any transmission. With a narrow barrier, actually, 1 of every 10,000 electrons is going to transmit. And that's a crazy difference for one, this astronomically forbidden thing to happen. That is, there is truly, for the transmission coefficient, T has an exponential sort of non-linear response to barrier width. That is, a really small change in barrier width leads to a crazy diminishment or increase in transmission. And it's really over the difference of 1 and 5 nanometers in this particular example. And this can be utilized if you have a surface of like a material with a bump on it of about, say, 3 nanometers. And if you take a scanning tip that is 5 nanometers roughly from the surface, and you move this tip over the surface, then when this tip is above here, your tunneling coefficient is, I don't roughly know the answers, but it's 10 to the 20th times as likely to tunnel here than here. And this is the basis of the scanning tunneling microscope. You can resolve features on a surface that are 3 nanometers tall, right? So a couple of atoms tall, but you can actually, because of this sensitive dependence, this exponential nonlinear response to barrier width. The barrier width is the distance between the surface and the tip of the scanning tunneling microscope. Right, that's W. Because of this nonlinear response, you can see fractions of a nanometer easily.